So in this lesson, we're going to learn about how to determine the number of significant figures in a measurement. So first of all, any measurement will have some amount of uncertainty, and that needs to be expressed somehow, and that is through the concept of significant figures. Let's start off first by defining things that do not have any uncertainty. So if you have something that you can count that's a small number that everybody could agree on. So for example, if you had 5 dimes in your pocket, you pull them out, it's easy to count, anybody looking at it would agree with you, then there's no uncertainty in the number of dimes in your pocket. So it's true for anything that you can count very easily. Also, relations that are well defined, for example, the C here stands for centi, which means 1 divided by 100. So that's an exact definition. So 100 centimeters exactly equals 1 meter. In that case, the 100 and the 1, these numbers, we do not think about them in terms of significant figures. We just say that there is no uncertainty in that relation. And then finally, numbers that you see in equations, for example, the radius of a circle is equal to 1/2 times its diameter. Both the 1 and the 2 have no uncertainty in them either. In fact, probably the easiest way to think of this is any time you look at numbers in an equation, if there are no units associated with them, like centimeters or meters, then there's no uncertainty in it. And the other thing is if you see a relation that's well defined, there's no uncertainty. Now, let's take a look at some measurements where there always will be some uncertainty. If we measure the length of this tuna, we can use two different length measuring devices. They both, so this ruler is measuring things in terms of tens of centimeters on the rulings. The one below here has tens of centimeters, but it also has rulings within 10 centimeters. There's 10 rulings within 10 centimeters. Each one is 1 centimeter each. So when we go to measure using this cruder ruler, we can say that the length of the fish is somewhere between 50 to 60 centimeters. Now we need to guess where it is between 50 and 60. And if you drew, here's about the halfway point. So this would be about 55 centimeters, where you can say, well, it's somewhere between 50 and 55 centimeters. But exactly where is it? You have to sort of guess. So the best guess is 53 centimeters. So in any measurement, all of the numbers in front of the last one are well known. It is always the last digit that is a best guess. So looking at the line, it's probably somewhere between 53 and 54 centimeters, but we can't really be sure which one it is. If we look at the more precise measuring device, there's more information content that we can gain from this ruler. We can narrow it down further, and it's somewhere between 53 and 54 centimeters. And so we now need to guess where in between 53 and 54 it is. And if we look at the line, maybe the best guess, it's somewhere, maybe it could be 53.4, maybe 53.5 centimeters. We're guessing here that it's 53.5. So essentially, it depends on the measuring device that you're using to provide the information content for the measurement. Now, both of these measurements are using a device called an analog measuring device, where you actually have to interpolate that last digit or guess on where it is. Digital devices will actually provide numbers for you. So when you go into the laboratory to measure mass, for example, you will be measuring things in grams in our laboratory, and our balances are good to 0.001 grams. So when you measure something, you might get 5.678 grams. Then this, even though it's giving you that number, this is uncertain. a little bit. Sometimes it'll even fluctuate between 7 and 9 a little bit. So we're saying that we know this value to plus or minus 0.001 grams. We're saying that we know this digit to plus or minus 1 centimeter, and we know this measurement to plus or minus 0.1 centimeter. So again, looking at these two measurements, this is more precise. It's giving us a little more information than this one. So I hope this allows you to perceive that in any measurement, it's always inexact, and it's that last digit that you're estimating. So counting significant figures, we would say that this measurement has 2 significant figures, this one has 3, and now we need to examine rules for establishing how many you have in a measurement. So to summarize the things that we've just been talking about, when you look at a measured value, the numbers in front of the last one are certain. It is the last one that's estimated. So again, we would know this value roughly to plus or minus 0.001 of whatever units this measurement is associated with. All right, now looking at our rules for counting them, you should always look for the first number that's not 0. So in this measurement, it starts at the 3, and you go to the very last digit. This is the one that's uncertain. This is the guess. So there's 1, 2, 3, 4 significant figures here. Again, for this measurement, you start at the first number that's not 0, the 5, and this is the one that we're guessing on. So this is 2 significant figures. Here we have 1, 2, 3 significant figures, and here we have 1, 2, 3, 4, 5 significant figures. Now, when we deal with zeros, there's some things that you have to keep track of. But again, our rule is going to stand as follows. Start with the first number that's not 0, that would be the 5, and count to the last digit that is expressed, which is this one. This is our uncertainty. So we have 1, 2, 3 significant figures. Here, we start with the first number that's not 0, the 2. Here's where our guessed number is, and so we have 4 significant figures here. Now, when we look at this number, the first number that's not 0 is the 1 here. So we don't count the 0 in front. We start here and go again to the last digit that's expressed. That would be 1, 2, 3, 4 significant figures. And here we have 1, 2, 3, 4, 5 significant figures. So what we find is that the interior zeros are not significant. That's not really a rule you need to remember. What you should remember is always start from the first number that's not 0 and go to the last digit that is expressed in the number. Now, there is one thing that we haven't talked about yet, that there's a certain exception for that last digit. If the last digit is a 0, there's some more rules that we need to look into. So we're going to talk about those next. But just to paraphrase what we're talking about here, we know this value to plus or minus 0.1 millimeters. We know this to plus or minus 1 minute. We know this to plus or minus 0.0001 pounds. And we know this value to plus or minus 0.00001 meter. Okay? All right, applying the rules that we've been looking at, the first non-zero number is there. So we only have 1 significant figure. Here we start at the 1. We have 3 significant figures. Here we start at the 4. We only have 2. And here we start there. And here we have 3 significant figures. So again, remember the rule. Start from the first number that's not 0. Now, let's talk about what these zeros are doing between the first number that's not 0 and the decimal point. All these zeros are doing is acting as what we call a placeholder for the decimal point. Where is it relative to this number? It's placing the 8 in the thousandths place here, it's placing the 1 in the hundredths place. So in terms of information content in the measurement, all it's doing is expressing how large or how small the first piece of information is, which is that first non-zero number. So as a consequence, it should make sense that these are not significant in terms of information content for counting the number of significant figures. Now, we mentioned that let's look at this first measurement. You always start from the first number that's not 0, and you always go to the last digit that we talked about, right? Well, this last digit happens to be a 0. Is it significant or not? Well, it depends where it is. If it's after a decimal point, it is. If there is no decimal point, these are not significant. Now let's talk about why. Imagine we wrote this value instead, 48,600.5 milliliters. If we wrote that, we're saying that we know this value to plus or minus 0.1 milliliters. But writing it with the 0 after it isn't changing the value of the measurement, but it's changing the information content, because what it implies is that we know this value to plus or minus 0.01 milliliters. So in other words, we constrain what this measured values, the range of possible values. This could be 600.6 or 600.4 milliliters. This is good to 600.49 or 0.51 milliliters. So the 0 is significant here. I hope you can understand why. Now let's look at these zeros. Well, I'm not putting a decimal point there, but you know it's there. They're acting like placeholders for the zeros, just like in this example. It's expressing where the last bit of information is, which is right here, the 5, is relative to the decimal point. The last bit of information, this is the digit that's being guessed at, is in the thousandths place. So we know this is 25,000 centimeters plus or minus 1,000 centimeters. You're going to have to get used to this, okay? These zeros are not significant. They're just acting as a placeholder for where the 5 place is. It's in the thousandths place. Likewise, so this is only 2 significant figures. Likewise, this is only 1 significant figure. The zeros are acting as a placeholder for that decimal point. This is plus or minus 100 kilograms. So we don't know this value very well. It could be 100. It's somewhere between 100 and 300 kilograms, and that's our best guess. When we look at this value, we start our count here and we end there. That's our best guess. So we know this value to plus or minus 1,000 grams. So this is 1, 2, 3, 4, 5 significant figures. Now, if we want to express that the 0 at the end here, just like in this case, is significant, we put a decimal point here. What that's implying is that this is our guessed digit. We know this to plus or minus 1 gram. Here we know it to plus or minus 1,000 grams. By putting the decimal point there, we're saying that all of these digits, including that last one, are significant. So this is 3, 6, 7, 8. This has 8 significant figures in it. Now, we're going to get a little ahead of ourselves here, but let's look at an arithmetic operation which will further illustrate what we mean by the information content and the uncertainty in a measurement. The population of the U.S., this is dated, so our best estimate today is about 335 million. Okay? So I'm not going to get into the details of how well we know this from the U.S. Census, but just for the sake of argument, let's just say that we know this value to plus or minus 1 million. Which is what is being implied when we write 335 million, right? It could somewhere between 334, 336 million. Now let's say someone came into the country and the Census Bureau counted it. Would it make sense to make, when we do this calculation, to write 335 million in 1? I want you to think about it for a minute. This value is good to 1 million. Adding a single entity to a number that's uncertain to plus or minus 1 million is not going to change the information content in this value. We would still just keep it at 335 million. We wouldn't change it. Okay? We'll go into arithmetic operations of dealing with this here in a moment, but I hope that serves to illustrate the meaning of uncertainty in a measurement. Now let's go ahead and look at scientific notation. So we express numbers in scientific notation for dealing with very large or very small numbers, and in so doing, we're also going to express uncertainty in that measurement. Generally, scientific notation will have one digit followed by a decimal point, and then either 1, 0, or 1 or more digits after the decimal point multiplied by a base 10 raised to the power of n. So let's look at this. If you've got a liter of helium gas, say in this Erlenmeyer flask, there are roughly 26.8 sextillion helium atoms. Look at all the zeros in here. If we want to express this number in scientific notation, and we do because no one really wants to write out this massively large number, in scientific notation it's much more compact. We would start by counting how many powers of 10 we need to multiply our number by. So we need to get it in this notation. 2.68 times 10 to some power of something. So here's my decimal point. Every time I move it to the left, I have to multiply by 10 so that I don't change the number. So for example, if I move this over 1, 2, 3, and now I remove those zeros, I've changed my number. To keep the number from changing, take all of this information and multiply by 1,000. So I would write multiply by 10 to the third. Okay? So every time I move this over a decimal point, that's 1 power of 10. So that's 3, 6, 9, 12, 15, 18, 21, and now to get it in the right format would be 22 times I have to do that. So now the number there is 22. So we have 2.68 times 10 to the 22nd atoms of helium. How many significant figures do we have? We start with our non-zero number there, and we end there. Remember, these zeros are not significant. Okay, we're not putting a decimal point at the end there. So there's only 3 significant figures in this number. Scientific notation is also a very good way of expressing uncertainty in very big numbers. We can also do this with small numbers. So this is a model representation for the molecule called benzene. It has the formula: 6 carbon atoms, 6 hydrogen atoms. The 6 carbon atoms form a hexagon and are bonded together, and there's 1 hydrogen bonded to each carbon atom. Now we want to express the length of a carbon-carbon bond, which right now is expressed in meters. Well, meters is not a good unit for talking about small lengths, so we want to express this in scientific notation and or change the unit. So here, if I move the decimal point in this direction to the right, I am in effect making the number larger by 10 each time, which means that I need to get the decimal point there. I need to express it like this, to some number here. So if I move to the right, each time I'm making the number smaller by 10, larger by 10, I need to make the number smaller by 10 by dividing by 10. So remember, every time you divide by 10, that's equal to 10 to the minus 1. So let's count them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this becomes times 10 to the minus 10th meters. So think about it. Every time we move to the right, we're multiplying by 10 so that we don't change the number. We need to divide by 10 each time we go through. Okay, so that's why we have the minus sign there, which is actually divided by 10. If we want to convert it to a natural unit, and we're not going to show you how to do this right now, the nanometer or the picometer, pico means 10 to the minus 12. I don't think that's one of the units that you need to memorize, but nano means 10 to the minus 9. In here. Actually, let me back that up. Yeah, so in our unit conversion, we have 10 to the 9th, so nanometers is equal to 1 meter. And then if we divide by 10 to the 9th on both sides, we have 1 nanometer is equal to 1 divided by 10 to the 9th meters, which is equal to 10 to the minus 9th meters. Okay? So backing up, going back and looking at expressing these values in scientific notation, 25,000 centimeters, if we change this to scientific notation, we move it to the right 1, 2, 3, 4 decimal places. So this is 2.5 times 10 to the 4th. If in doubt, you could always take this value and convert it to scientific notation in your calculator. You need to learn how to do that. And you can see that it's expressed to only 2 significant figures. If we did this one, this would be 2 times 10 to the 2nd power. We have only 1 significant figure. When we convert this one, we move the decimal point over 3 times, 6 times, 7 times. So this is 2.5005 times 10 to the 7th. And now this value, converting it to scientific notation, all of these digits would be expressed. Okay? That last 0 there is significant when we put that decimal point there. And then finally, different scientific calculators allow you to convert a standard number into scientific notation a variety of different ways. You should look for a button labeled EXP or EE. You don't want to look for this. 10 to the x is the anti-log. Do not use that. Instead, for this particular calculator, we want to use this button. For example, if your calculator reads 7.45 e minus 17, what that means, the e means times 10 and then raised to the power of minus 17. To enter this number in your calculator, the way you would do it is you put in 7.45, hit the EXP or the EE button, and then put in here, there's a number of ways of doing it. You can either put 17 followed by that, or go ahead and put that in first and then 17. But either way, you need to get used to learning how to do this in your own calculator.